Hello dear friends, myself Sachin Kothaude. Today we are going to see the topic chemical kinetics, which is important for second year students semester 4 related to the subject physical pharmaceutics 2. Now what is chemical kinetics? Chemical kinetics, it is the study of rate of the reaction or how fast the chemical reaction it takes place. So what is the rate of the reaction or reaction rate? It is the change in amount or concentration of the reactant or the product per unit time, that is decrease in concentration of the reactant per unit time, which is equals to the increase in concentration of the product per unit time. Next is the rate law. Rate law, the statement of the rate law is that at a fixed temperature, the rate of the given reaction, it depends on the concentration of the reactant. So rate law, by study of that numerous reactions, it is shown that the rate of the reaction is directly proportional to the reactant concentration. Now each concentration being raised to the some power. For example, that rate is directly proportional a raised to n, which is also written as rate is equals to k into a raised to n. So for the reaction 2a plus b, it gives the product. So that rate of that reaction with respect to a and b is determined, so which is written as rate is equals to k into a raised to m into b raised to n. So these expressions 1 and 2 will tell us the relationship between the rate of the reaction and the reactant concentration. So some examples of the rate law, that is one example we'll see that 2N2O5, it gives 4NO2 plus O2. So here the rate law for this reaction can be expressed that rate is equals to K into concentration of N2O5. Now here the K is called as a reaction rate constant, proportionality constant K, and the another examples are there. Next is order of the reaction. Now order of reaction, it is defined as the sum of the powers of concentration given in rate law. Now let us consider the example of the reaction which has been given in the rate law, that rate is equals to K into A raised to M into the concentration of B raised to N. So for this rate law, we'll express the order as, that is M plus N, that is the concentration, that powers to the concentration M and powers to the concentration B is N. So M plus N, it gives the order of that reaction. And the overall order of that reaction, it is ranges from 1 to 3, and it can be a fractional value also. So the example of that order of reaction, we'll see one example, that is rate is equals to rate law, that rate is equals to K into concentration of N2O5. So here raised to the power of that N2O5, it is not given, that means it is 1. Okay, so reaction order of that is 1. Another example is rate is equals to K into H2 into I2. Okay, so here M plus N, that is 1 plus 1, it is equals to the 2. So these reactions may be classified according to their order, that is M plus N, if it is equals to 1, then it is a first order reaction. M plus N is equals to 2, then it is a second order reaction. M plus N is equals to 3, it is the third order reaction. Then another one, next is different orders of the reaction. We have seen that first order, second order, there is a zero order reaction is also there. Now what is zero order reaction? It is a reaction in which the reactant whose concentration does not affect the reaction rate, which is not included in the rate law, So in effect, that concentration of that reactant has the power 0. So A raised to 0 equals to 1. So a zero order reaction is the one whose rate is independent of the concentration of the reactant. For example, NO2 plus CO, it gives NO plus CO2. Now here the rate law for this reaction is expressed as rate is equals to K into NO2 raised to 2. NO2 raised to 2. Here carbon monoxide whose concentration does not affect the rate of that reaction, so it is not included in the rate law. So this reaction is zero order reaction. Okay, so here that rate does not depends on the concentration of CO, so this is not included in the rate law, and the power of CO is understood to be 0, and the reaction is zeroth order with respect to the CO, and the reaction is second order with respect to the NO2. So overall order of that reaction is 2 plus 0 equals to 2, but this reaction is zero order because it is independent of concentration of CO. The next point is molecularity of a reaction. So there are different types of that reactions: elementary reaction and complex reaction. So elementary reaction, it is the reaction which occurs in a single step, which does not occur in more than one step. That is single step reactions. These are called as elementary reactions. And the second type of the reaction is the complex reaction, which occurs in more than one step. That type of reactions are called as complex reactions. Now molecularity of an elementary reaction. Elementary reaction means which occurs in a single step. So molecularity of the elementary reaction, it is defined as the number of reactant molecules involved in a reaction. That is called as molecularity of the reaction. Now again the molecularity can be given as 1, 2, 3, etc. according to as 1, 2 or 3 reactant participating in the reaction. So elementary reaction having molecularity 1, 2 and 3, these are called as unimolecular, bimolecular and termolecular respectively. Okay, so here there are some examples are given. Unimolecular reactions, Br2, it gives 2Br. Then bimolecular reaction, that is the number of reactant molecules 2, A plus B or A plus A, it gives the product. So the example of that is ethyl acetate plus water, it gives acetic acid plus ethyl alcohol. And the termolecular reaction, that is molecularity is 3, 2NO plus O2, it gives 2NO2. Now why the high molecularity reactions are very rare? Now the reason behind that, more of that reactions. Okay, now for example, if one or two or most of the three molecules, if they are involved in the reaction, so the reactions involving 4 or more molecules, these are very rare. Okay, now this rarity of the reaction with the high molecularity can be explained on the basis of the kinetic molecular theory. Now according to this theory, the rate of the chemical reaction is proportional to the number of collisions taking place between the reacting molecules, and the chances of simultaneous collision of the reacting molecules will go on decreasing with the increasing number of the molecules. Like for example, if the possibility of the 3 molecules colliding together is much less than the case of bimolecular collision. So for a reaction of the molecularity 4, the 4 molecules must come closer to each other and then collide with one another at the same time. The possibility of that is very less. So